On Colors. On Colors by Aristotle, translated by Edward Forster and Thomas Loveday. De Coloribus. 1. Simple colors are the proper colors of the elements, id est, of fire, air, water, and earth. Air and water, when pure, are by nature white, fire and the sun yellow, and earth is naturally white. The variety of hues which earth assumes is due to coloration by tincture, as is shown by the fact that ashes turn white when the moisture that tinged them is burnt out. It is true they do not turn a pure white, but that is because they are tinged afresh in the process of combustion by the smoke which is black, and this is the reason why lye mixture turns yellow, the water being colored by hues of flame and black. Black is the proper color of elements in process of transmutation. The remaining colors, it may easily be seen, arise from blending by mixture of these primary colors. Darkness is due to privation of light, for we see black under three different conditions. Either 1. The object of vision is naturally quite black, for black light is always reflected from black objects, or 2. No light at all passes to the eyes from the object, for an invisible object surrounded by a visible patch looks black, and 3. Objects always appear black to us when the light reflected from them is very rare and scanty. This last condition is the reason why shadows appear black. It also explains the blackness of ruffled water, exempli gratia, of the sea when a ripple passes over it. Owing to the roughness of the surface, few rays of light fall on the water, and the light is dissipated, and so the part which is in shadow appears black. The same principle applies to very dense cloud, and to masses of water and of air, which light fails to penetrate, for water and air look black when present in very deep masses, because of the extreme rarity of the rays reflected, the parts of the mass between the illuminated surfaces being in darkness and therefore looking black. There are many arguments to prove that darkness is not a color, but merely privation of light, the best being that darkness, unlike all other objects of vision, is never perceived as having any definite magnitude or any definite shape. Light is clearly the color of fire, for it is never found with any other hue than this, and it alone is visible in its own right, whilst all other things are rendered visible by it. But there is this point to be considered, that some things, though they are not in their nature fire, nor any species of fire, yet seem to produce light. So we cannot say, in the same breath, the color of fire is identical with light, and yet light is the color of other things besides fire. But we can say, this hue is to be found in other things besides fire, and yet light is the color of fire. Anyhow, it is only by aid of light that fire is rendered visible, just as all other objects are made visible by the appearance of their color. The color black occurs when air and water are thoroughly burnt by fire, and this is the reason why burning objects turn black, as, exempli gratia, wood and charcoal when the fire is put out, and smoke from clay, as the moisture is gradually secreted and burnt. This is also why the blackest smoke is given off by fat and greasy substances like oil and pitch and resinous wood, because these objects burn most completely, and the process of combustion is most continuous in them. Again, things turn black through which water percolates, if they first become coated with lichen, and then the moisture dries off. The stucco on walls is an example of this, and much the same applies to stones under water, which get covered with lichen and turn black when dried. This, then, is the list of simple colors. 2. From these primary colors, the rest are derived, in all their variety of chromatic effects, by blending of them and by their presence in varying strengths. The different shades of crimson and violet depend on differences in the strength of their constituents, whilst blending is exemplified by mixture of white with black, which gives gray. So a dusky black mixed with light gives crimson. For observation teaches us that black mixed with sunlight or firelight always turns crimson, and that black objects heated in the fire all change to a crimson color, as exempli gratia, smoky tongues of flame, or charcoal when subjected to intense heat, are seen to have a crimson color. But a vivid bright violet is obtained from a blend of feeble sunlight with a thin, dusky white. That is why the air sometimes looks purple at sunrise and sunset, for then these conditions are best realized, the air being dusky and the impinging rays feeble. So too the sea takes a purple hue when the waves rise, so that one side of them is in shadow. The rays of the sun strike without force on that slope, and so produce a violet color. The same thing may also be observed in birds' wings, which get a purple color if extended against the light, but if the amount of light falling on them is diminished, the result is the dark color called brown, whilst a great quantity of light blended with primary black gives crimson. Add vividness and luster, and crimson changes to flame color. For it is after this fashion that we ought to proceed in treating of the blending of colors, starting from an observed color as our basis, and making mixtures with it. But we must not assign to all colors a similar origin, for there are some colors which, though not simple, bear the same relation to their products that simple colors bear to them, inasmuch as a simple color has to be mixed with one other color to produce them. And when the constituents are obscure in the compound product, we must still try to establish our conclusions by reference to observation. For whether we are considering the blend which gives, say, violet or crimson, or whether we are considering the mixtures of these colors which produce other tints, we must explain their origin on the same kind of principles, even though they look dissimilar. So we must start from a color previously established, and observe what happens when it is blent. Thus we find that wine color results from blending rays of sunlight with pure lustrous black, as may be seen in grapes on the bunch, which grow wine-colored as they ripen, for as they blacken, their crimson turns to a violet. After the manner indicated, we must treat all differences of colors, getting comparisons by moving colored objects, keeping our eye on actual phenomena, assimilating different cases of mixture on the strength of the particular known instances in which a given origin and blending produce a certain chromatic effect, and verifying our results. But we must not proceed in this inquiry by blending pigments as painters do, but rather by comparing the rays reflected from the aforesaid known colors, this being the best way of investigating the true nature of color blends. Verification from experience and observation of similarities are necessary if we are to arrive at clear conclusions about the origin of different colors, and the chief ground of similarities is the common origin of nearly all colors in blends of different strengths of sunlight and firelight, and of air and water. At the same time, we ought to draw comparisons from the blends of other colors, as well as the primary, with rays of light. Thus charcoal and smoke, and rust and brimstone, and birds' plumage blent, some with firelight and others with sunlight, produce a great variety of chromatic effects. And we must also observe the results of maturation in plants and fruit, and in hair, feathers, and so on. 3. We must not omit to consider the several conditions which give rise to the manifold tints and infinite variety of colors. It will be found that variations of tint occur: 1. Because colors are introcepted by varying and irregular strengths of light and shade. For both light and shade may be present in very different strengths, and so whether pure or already mixed with colors, they alter the tints of the colors they introcept. Or 2. Because the colors blent vary in fullness and in effectiveness. Or 3. Because they are blent in different proportions. Thus violet and crimson and white and all colors vary very much both in strength and in intermixture and purity. 4. Difference of hue may also depend on the relative brightness and luster or dimness and dullness of the blend. Luster is simply continuity and density of light. Exempli gratia, we have a glistening gold color when the yellow color of sunlight is highly concentrated and therefore lustrous. That explains why pigeons' necks and drops of falling water look lustrous when light is reflected from them. Again, 5. Some objects change their color and assume a variety of hues when polished by rubbing or other means, like silver, gold, copper, and iron when they are polished, and some kinds of stones give rise to different colors, like. Footnote: the name of the stone has dropped out. Galactites, slate, and other substances have been suggested. Prantl rightly observes that the argument requires lambanusi in place of graphusi. End footnote. Which are black but make white marks. This is because the original composition of all such substances is of small, dense, and black particles, but in the course of their formation they have been tinged, and all the pores through which the tincture passed have taken its color, so that finally the whole material appears to be of that color. But the dust that is rubbed off from them loses this golden or copper color, or whatever the hue may be, and is quite black, because rubbing breaks up the pores through which the tincture passed, and black is the original color of the substance. The other color is no longer apparent because the coloring matter is dissipated, and so we see the original natural color of the material, and this is why these substances all appear black. But when rubbed against a smooth and even surface, as exempli gratia against a touchstone, they lose their blackness and get back their other color, which comes through where the lines of the tincture in the pores are unbroken and continuous. 6. In the case of objects burning, dissolving, or melting in the fire, we find that those have the greatest variety which are dark in color and give off a thin, hazy smoke, such as the smoke of brimstone or rusty copper vessels, and those which, like silver, are dense and smooth. 7. Apart from these cases, variety of hue is characteristic of all dark, smooth objects, such as water, clouds, and birds' plumage. For these last, owing to their smoothness and the variety of blends into which the impinging rays of light enter, show various colors, as also does. Footnote. As Prantl says, Scotus is certainly corrupt, and the name of some smooth, dark substance has dropped out. End footnote. 8. Lastly, we never see a color in absolute purity. It is always blent, if not with another color, then with rays of light or with shadows, and so it assumes a new tint. That is why objects assume different tints when seen in shade and in light and sunshine, and according as the rays of light are strong or weak, and the objects themselves slope this way or that, and under other differential conditions. Again, they vary when seen by firelight, or moonlight, or torchlight, because the colors of those lights differ somewhat. They vary also in consequence of mixture with other colors. For when colored light passes through a medium of another color, it takes a new tinge. For if light falls on a given object and is colored by it, say crimson or herb green, and then the light reflected from that object falls on another color, it is again modified by this second color, and so it gets a new chromatic blend. This happening to it continuously, though imperceptibly, light, when it reaches the eye, may be a blend of many colors, though the sensation produced is not of a blend, but of some color predominant in the blend. This is why objects under water tend to have the color of water, and why reflections in mirrors resemble the color of the mirrors. And we must suppose that the same thing happens in the case of air. Thus, all hues represent a threefold mixture of light, a translucent medium, exempli gratia, water or air, and underlying colors from which the light is reflected. A translucent white medium, when of a very rare consistency, looks hazy in color, but if it is dense, like water or glass, or air when thick, a sort of mist covers its surface, because the rays of light are inadequate at every point on it owing to its density, and so we cannot see the interior clearly. Air seen close at hand appears to have no color, for it is so rare that it yields and gives passage to the denser rays of light, which thus shines through it. But when seen in a deep mass, it looks practically dark blue. This again is the result of its rarity, for where light fails, the air lets darkness through. When densified, air is, like water, the whitest of things. 4. Coloration may also be due to a process of tincture or dyeing, when one thing takes its hue from another. Common sources of such coloration are the flowers of plants and their roots, bark, wood, leaves or fruit, and again earth, foam, and metallic inks. Sometimes coloration is due to animal juices, exempli gratia, the juice of the purple fish, with which clothes are dyed violet. In other cases, to wine, or smoke, or lye mixture, or to sea water, as happens, for instance, to the hair of marine animals, which is always turned red by the sea. In short, anything that has a color of its own may transfer that color to other things, and the process is always this: that color, leaving one object, passes with moisture and heat into the pores of another, which, on drying, takes the hue of the object from which the color came. This explains why color so often washes out. The dye runs out of the pores again. Furthermore, steeping material to be dyed in different astringent solutions during the dyeing produces a great variety of hues and mixtures, and these are also affected by the condition of the material itself, in much the same way that blending of colors was shown in the last chapter to be affected. Even black fleeces are used for dyeing, but they do not take so bright a color as white. The reason is that whilst the pores of the wool are tinged by the dye that enters them, the intervals of solid hair between the pores do not take the color; and if they are white, then in juxtaposition to the color of the pores they make the dye look brighter, but if they are black, they make it look dark and dull. For the same reason, a more vivid brown is obtained on black wool than on white, the brown dye blending with the rays of black, and so looking purer. For the intervals between the pores are too small to be separately seen, just as tin is invisible when blent with copper in bronze, and there are other parallel cases. These, then, are the reasons for the changes in color produced by dyeing. 5. As for hair and feathers and flowers and fruit and all plants, it is abundantly clear that all the changes of color which they undergo coincide with the process of maturation. But what the origins of color in the various classes of plants are, and what kinds of changes these colors undergo, and from what materials these changes are derived, and the reasons why they are thus affected, and any other difficulties connected with them, in considering all these questions, we must start from the following premises. In all plants, the original color is herb green. Thus, shoots and leaves and fruit begin by taking this color. This can also be seen in the case of rainwater. When water stands for a considerable time and then dries up, it leaves a herb green behind it. So it is intelligible why herb green is the first color to form in all plants. For all water in process of time first turns yellow-green on blending with the rays of the sun; it then gradually turns black, and this further mixture of black and yellow-green produces herb-green. For, as has already been remarked, moisture becoming stale and drying up of itself turns black. This can be seen, for example, on the stucco of reservoirs. Here all the part that is always under water turns black, because the moisture, as it cools, dries up of itself; but the part from which the water has been drawn off, and which is exposed to the sun, becomes herb green, because yellow mingles with the black. Moreover, with the increasing blackness of the moisture, the herb green tends to become very deep and of a leek green hue. This is why the old shoots of all plants are much blacker than the young shoots, which are yellower, because the moisture in them has not yet begun to turn black. In the older shoots the growth being slow and the moisture remaining in them a long time, owing to the fact that the liquid, as it cools, turns very black, a leek green is produced by blending with pure black. But the color of shoots in which the moisture does not mix with the rays of the sun remains white, unless moisture has settled in them and dried and turned black at an earlier stage. In all plants, therefore, the parts above ground are at first of a yellow green, while the parts under the ground, namely the lower portions of the stalks and the roots, are white. The shoots, too, are white as long as they are underground, but if the earth be removed from round them, they turn herb green. And all fruit, as has been already said, becomes herb green at first, because the moisture which passes through the shoots into it has a natural tendency to assume this color, and is quickly absorbed to promote the growth of the fruit. But when the fruit ceases to grow because the liquid nourishment which flows into it no longer predominates, but the moisture, on the contrary, is consumed by the heat, then it is that all fruit becomes ripe, and the moisture already present in it being heated by the sun and the warmth of the atmosphere, each species of fruit takes its color from its juice, just as dyed material takes the hue of the coloring matter in which it is steeped. This is why fruits color gradually, those parts of them which face the sun and heat being most affected. It is also the reason why all fruits change their color with the changing seasons. This explanation agrees with the observed facts. For all fruits, as soon as they begin to ripen, change from herb green to their normal proper color. They become white and black and gray and yellow and blackish and dusky and crimson and wine-colored and saffron, in fact, assume practically every variety of color. Since most hues are the result of the blending of several colors, the hues of plants must certainly also be due to the same blends, for the moisture percolating through the plants washes and carries along with it all the ingredients on which their colors depend. When this moisture is heated up by the sun and the warmth of the atmosphere at the time of the ripening of the fruit, each of the colors forms separately, some quickly and some slowly. The same thing happens in the process of dyeing with purple, when, after breaking up the shell and extracting all the moisture from it, they pour it into earthenware vessels and boil it. At first, no definite color is noticeable in the dye, because, as the liquid boils more and more, and the colors still remaining in the vessels mix together, each of the hues gradually undergoes a great variety of alterations. For black and white and brown and hazy shades appear, and finally the dye all turns purple when the colors are sufficiently boiled up together. So, as a result of the blending, no other color is separately noticeable. This is just what happens with fruit. In many instances, because the maturing of all the colors does not take place simultaneously, but some colors form earlier and others later, changes from one to another take place, as in the case of grapes and dates. Some of these are crimson at first, but when black color forms in them, they turn to a wine color, and in the end they become of a dark bluish hue, when the crimson is finally mixed with a large quantity of pure black. For the colors, which appear late, when they predominate, change the earlier colors. This is best seen in black fruits, for, broadly speaking, most of them, as has already been remarked, first change from herb green to a pinkish shade and become reddish, but quickly change again from the reddish hue and become dark blue because of the pure black present in them. The presence of crimson is proved by the fact that the twigs and shoots and leaves of all such plants are crimson, because that color is present in them in large quantities, while that black fruits partake of both colors is clear from the fact that their juice is always of a wine color. Now, the crimson hues come into existence at an earlier stage in growth than the black. This is clear from the fact that pavement upon which there is any dripping, and generally speaking, any spot where is a slight flow of water in a shady place, always turn first from herb green to a crimson color, and the pavement looks as though blood had lately been shed over all the portion of it on which the herb green color has matured. Then, finally, this also becomes very black and of a dark bluish color. The same thing happens in the case of fruit. That change in the color of fruit occurs by the formation of a fresh color, which ousts the earlier one, can easily be seen from the following examples. The fruit of the pomegranate and the petals of roses are white at first, but in the end, when the juices in them are beginning to be tinged, as they mature, they alter their colors and change to violet and crimson hues. Other parts of plants have a number of shades. For example, the juice of the poppy and the scum of olive oil. For this is white at first, as is the fruit of the pomegranate, but after being white, it changes to crimson, and finally mingling with a large quantity of black, it becomes of a dark bluish hue. So too the petals of the poppy are crimson at their ends, because the process of maturation takes place quickly there, but at their base they are black, because this color is already predominant at that end, just as it predominates in the fruit, which also finally becomes black. In the case of plants which have only one color, white for example, or black, or crimson, or violet, the fruit always keeps a single kind of color, when once it has changed from herb green to another color. Sometimes the blossoms are of the same color as the fruit, as for instance in the pomegranate, the fruit and blossoms of which are both crimson, but sometimes they are of very dissimilar hues, as for example in the bay tree and the ivy, whose blossoms are always yellow, but their fruit respectively black and crimson. The same is true of the apple tree. Its blossom is white with a tinge of pink, while its fruit is yellow. In the poppy, the flower is crimson, but the fruit may be black or white, according to the different time at which the juices present in the plant ripen. The truth of the last statement can be seen from many examples, for, as has been said, some fruits come to differ greatly as they ripen. This is why the peculiar odors and flavors of flowers and fruits differ so much. This effect of the time of ripening is still more evident in the actual blossoms, for part of the same petal may be black and part crimson, or in other cases, part white and part purplish. The best example of all is the iris, for its blossom shows a great variety of hues according to the different states of maturation in its different parts, just as grapes do when they are already ripening. Therefore, the extremities of blossoms always ripen most completely, whilst the parts near the vital principles of the plant have much less color, for in some cases the moisture is, as it were, burnt out before the blossom undergoes its proper process of maturation. It is for this reason that the blossoms remain the same in color, while the fruit changes as it grows riper. For the former, owing to the presence of only a small amount of nutriment, soon overmature, while the fruit, owing to the presence of a large quantity of moisture, changes as it ripens to all the various hues which are natural to it. This can also be seen, as has already been remarked, in the process of color dyeing. When in dyeing purple, they put in the coloring matter from the vein of the purple fish. At first it turns brown and black and hazy, but when the dye has been boiled sufficiently, a vivid bright violet appears. So it must be from similar reasons that the blossoms of a plant frequently differ in color from its fruit, and that some pass to a stage beyond, whilst others never attain to their natural color, according as they do or do not mature thoroughly. For these reasons, then, blossoms and fruit differ from one another in their coloring. The leaves of most trees turn yellow in the end, because, owing to the failure of nutriment, they become dried up before they change to their natural color, just as some of the fruits also which fall off are yellow in color, because here too nutriment fails before they mature. Furthermore, corn, and in fact all plants, turn yellow in the end. This change of color is due to the fact that the moisture in them no longer turns black, owing to the rapidity with which it dries up. As long as it turns black and blends with the yellow green, it becomes herb green, as has already been said. But since the black is continually becoming weaker, the color gradually reverts to yellow green, and finally becomes yellow. The leaves of the pear tree and the arbutus and some other trees become crimson when they mature, but the leaves even of these, if they dry up quickly, turn yellow, because the nutriment fails before maturity is reached. It seems very probable, then, that the differences of color in plants are due to the above causes. 6. The hairs, feathers, and hides, whether of horses, cattle, sheep, human beings, or any other class of animals, grow white, gray, reddish, or black for the same reason. They are white when the moisture which contains their proper coloring is dried up in the course of maturation. They are black, on the other hand, as was the case in the other form of life, when, during their growth, the moisture present in the skin settles and becomes stale owing to its abundance, and so turns black. In all such cases, skin and hide become black. They are gray, reddish, and yellow, and so on, when they have dried up before the moisture in them has completely turned black. Where the process has been irregular, their colors are correspondingly variegated. So, in all cases, they correspond in color to the hide and skin. For when men are reddish in coloring, their hair too is of a pale red. When they are black, it is black. And if white leprosy has broken out over some part of the body, the hair on that portion is also always white, like the marking on dappled animals. Thus all hair and feathering follows the color of the skin, both regional hair and hair which is spread over the whole body. So too with hoofs, claws, beaks, and horns. In black animals they are black, in white animals they are white, and always because the nutriment percolates through the skin to the outer surface. A number of facts prove that this is the true cause. For example, the hair of all very young children is reddish, owing to scanty nutriment. That this is so is clear from the fact that the hair of infants is always weak and thin and short at first, but as they grow older, the hair turns black when the nutriment which flows into it settles, owing to its abundance. So too with the pubes and beard. When the hair is just beginning to grow on the pubic region and chin, It also is reddish at first, because the moisture in it, being scanty, quickly dries up. But as the nutriment is carried more and more to those regions, the hair turns black. But the hair on the rest of the body remains reddish for a considerable time owing to lack of nutriment. For as long as it is growing, it keeps on turning black, like the pubes and the hair of the head. This is clear from the fact that hairs which have any length are generally blacker near the body and yellower towards the ends, because the moisture which reaches these parts of them is very scanty and soon dries up. This is the case with the hair of sheep and horses, as well as with human hair. The feathers, too, of black birds are in all cases darker near the body and lighter at the ends. The same is the case with the parts about the neck, and, generally speaking, any part which receives scanty nutriment. This can be illustrated by the fact that before turning gray, all hair changes color and becomes reddish, because the nutriment again fails and dries up quickly. Finally, it becomes white, because the nutriment in it is completely matured before the moisture turns black. This can be illustrated from the parts of beasts of burden which are under the yoke. Here the hair always turns white, for in those parts, because, owing to the feebleness of the heat, they cannot draw up as much nourishment as the rest of the body, the moisture quickly dries up and turns white. So men tend especially to turn gray in the region of the temples, and generally speaking in any part which is weak and ailing. So too, white is the color to which, more than any other, a change tends to take place in instances of deviation from natural color. For example, a hare has been known before now to be white, while black hares have also been seen, and similarly white deer and bears have sometimes occurred. Similarly, white quails, partridges, and swallows. For all these creatures, when weak in their growth, come to maturity too soon owing to lack of nutriment, and so turn white. Similarly, some infants at birth have white hair and eyelashes and eyebrows, a circumstance which normally occurs when old age is coming on, and is then clearly due to weakness and lack of nutriment. Therefore, in most classes of animals, the white specimens are weaker than the black, for, owing to lack of nutriment, they overmature before their growth is complete, and so turn white, just as does fruit when it is unhealthy, for fruit is still more apt to get overmature through weakness. But when animals grow white, and at the same time are far superior to the rest of their species, as is the case with horses and dogs, the change from their natural color to white is due to generous nutriment. For in such animals the moisture, not settling long, but being absorbed in the process of growth, does not turn black. Such animals are soft and well covered with flesh, because they are well nourished, and white hairs, therefore, never change color. This is clear from the fact that black hairs, when the nutriment in them fails and matures too completely, turn reddish before they grow gray, but finally turn white. Yet some people hold that hair always turns black because its nutriment is burnt up by heat, just as blood and all other substances turn black under these conditions. But they are in error, for individuals of some species of animals are black from birth. Dogs, for example, and goats, and oxen, and generally speaking, those creatures whose skin and hair get nutriment from the very first, but they are less black as they get older. If their supposition were correct, this ought not to be the case, but it would necessarily follow that the hair of all animals would turn black at their prime when heat predominates in them, and that they would be more likely to be gray at first, for in the beginning the heat is always somewhat weaker than at the time when the hair begins to turn white. This is clear in the case of white animals also. Some of them are very white in color at birth, those namely which at first have an abundance of nutriment, the moisture in which has not been prematurely dried up. But as they grow older, their hair turns yellow, because less nutriment afterwards flows into it. Others are yellow at first, and are whitest at their prime. Similarly, birds change color when the nutriment in them fails. That this is the case can be seen in the fact that in all these animals it is the parts round the neck, and generally speaking, any parts which are stinted when the nourishment is scanty, which turn yellow. For it is clear that, just as reddish color turns black, and vice versa, so white turns yellow, and vice versa. This happens also in plants, some of which revert from a later stage in the process of maturation back again to an earlier stage. The best illustration of this is to be found in the pomegranate. At first its seeds are crimson, as are also its leaves, owing to the small amount of nourishment which matures completely. Afterwards they turn to a herb green, because a quantity of nutriment flows into them, and the process of maturation is less able to predominate than before. But in the end, the nutriment does mature, and the color reverts to crimson. To sum the matter up, in hair and feathers of every kind, changes always occur, either, as has already been remarked, when the nutriment in them fails, or when, on the contrary, it is too abundant. Therefore the age at which the hair is at its whitest or blackest varies in different cases, for even ravens' feathers turn yellow in the end, when the nutriment in them fails. But hair is never crimson, or violet, or green, or any other color of that kind, because all such colors arise only by mixture with the rays of the sun, and further, because in all hairs which contain moisture, the changes take place beneath the skin, and so they admit of no admixture. This is clear from the fact that no feathers have their distinctive coloring at first, but practically all gaily colored birds start by being black, the peacock, for example, and the dove and the swallow. It is only later that they assume all their varied colors, the process of maturation taking place outside their bodies in their feathers and combs and wattles. Thus in birds, as in plants, the maturation of the colors takes place outside the body. So too the other forms of animal life. Aquatic creatures, reptiles, and shellfish have all sorts and manners of coloring, because in them too the process of maturation is violent. From what has been set forth in this treatise, one may best understand the scientific theory of colors. End of On Colors.